In this lesson, we're actually going to prove that centripetal acceleration is towards the center in circular motion. So we'll start by simply drawing a full circle, right? And we know the definition for circular motion is the object is traveling along the tangent. So imagine at this particular point, the object is moving along the tangent here, right? So if we draw our little radius, that's the radius, and the object is here and is traveling along the tangent. And after a certain time t, the object has reached on this side. We know for circular motion that the velocity is changing, but which component of the velocity is changing is only the direction. The magnitude of the velocity, which is the speed, is the same. So let's draw that here. And we're going to use vectors to show this today. So if I was to do that perfectly 90 degrees, and look what I'll do, just to show that it's 90 degrees, I'll draw my right angle, okay? And because we're doing this to scale, I'm going to use the length of this ruler to show that this is the magnitude of this velocity. So that's my initial velocity. Let me put that as u. That's the initial velocity. After a certain time t, the object will then have covered an angular displacement of theta, or change in theta for that small period of time. Now, again, applying the same principle. So I just want to get my 90 degrees correct. And I recommend this, students, that you do this in the exam whenever you want to show to AQA that this is actually 90 degrees radial and tangential, even though you're off by a margin. But if you put that little square there, that shows that you know it should be 90 degrees. This is my final velocity. We do know that from the definition of acceleration, acceleration is the final speed, final velocity, take away the initial velocity divided by time. So that's my final velocity, that's my initial velocity. But in the definition for acceleration, it's the negative of the initial velocity. And you know, with vectors, if a vector is going in one direction, a negative of it will be in the opposite direction. So what's what I'm going to do now? That's the magnitude. I'm going to just bring it down here by the same amount. Okay, so I'm going to delete that, erase it. Just making sure, so that's, there you go. Dear. So that's my final velocity. That's my final velocity v. And my initial velocity u is like this. However, minus u would be in the opposite direction. And we know the principle for vectors. I'm starting off my vector here. That's my final velocity. And my initial velocity, if I get that perfectly horizontal, I'll find that. Is that perfectly horizontal? It's hard to judge, but let's put it here. I've now taken this u and I've flipped it in the other direction. So this is now my minus u. Well, what does that show you? Final velocity, take away initial velocity, and let's say that's within 1 second, it actually travels that distance, okay? It goes from point A to point B. So the velocity would have been final velocity, take away initial velocity. It started off here, and it actually finished right there. So how do we do vectors? Resultant vectors are drawn from start to finish. There you go. So that's my resultant vector. And look at it. It's actually pointing in towards the center. Just some margin. It's actually pointing towards the center. So this proves that acceleration is towards the center, even though the object is traveling tangentially. And we represent resultant by double arrows, with the actual initial and final velocity or single arrows. Okay, so I hope that gets your head around centripetal acceleration being towards the center. We have used the principle of vectors to prove that. There are other methods that you can use. In our next video, I'm actually going to derive the equation for acceleration is equal to v squared over r